Hello students, our second chapter in the first section is nuclear transformation. Nuclear transformation includes what are the important radionuclides and why they are decaying, and what is the radioactivity decay, what are the kinds of radioactivity, half-life, mean life, then what are the different types of nuclear transformations like alpha decay, beta decay, etc. And also finally, we go through nuclear fission, nuclear fusion, nuclear reactors, fusion reactors, etc. So, this is a picture of the interior of a tokamak fusion test reactor at the Princeton Plasma Physics Laboratory in 1993 December. This reactor produced 6.2 megawatt of fusion power for 4 seconds from a deuterium-tritium plasma confined by strong magnetic field. Now, the important points are all nuclei can be transformed by reactions with nucleons or other nuclei that collides with them. So, nuclei can be transformed. That is the important point by reactions. Okay. All complex nuclei are generated through successive nuclear reactions. So, radioactive decay was discovered in 1896 by Antony Henry Becquerel. This word you may be familiar with. Now, the important features of radioactive decay are: first point is that elements are not immutable. That means when a nucleus undergo alpha or beta decay, its atomic number changes from one value to another value and it becomes an entirely different element. That means elements are not immutable. You can convert one element into another. The second feature is that energy liberated during radioactive decay comes from within the individual nuclei without external excitation. So this energy liberated as was later experimentally or it was explained by the fact of mass energy relation given by Einstein. Then the third point is that it is a statistical process that it obeys chances. Okay, the law of chances is explained. Now the identification of the components of nuclear radiations. This is a radium sample. Radium sample is kept in a lead box. This is kept in a magnetic field. Magnetic field is represented as this cross mark. This cross mark indicates that the magnetic field is into this plane, perpendicularly into the plane of this paper. Okay. So in such an arrangement, you can find the alpha particle path like this. This is the gamma ray path. This is the beta particle path. So we analyze that alpha particles are deflected to the light, hence they are positively charged. So we identify alpha particles as positively charged particles. Beta particles are deflected to the right, hence they are negatively charged. And gamma rays are not affected, hence they are uncharged. Right? The 5 kinds of radioactive decay are: first one is alpha particle decay. So the decay in which alpha particle is involved is alpha particle is a helium nuclide He24. Here we exclude the electrons outside. The 2 electrons outside the helium atom is excluded and this is the helium nuclei is referred to as alpha particle. Now the beta particle is an electron. Okay. Gamma particle is high energy photon. Then there is positron emission, electron capture. These are the 5 kinds of radioactive decay. Now we compare the strength of alpha, beta and gamma radiations. So here is a cardboard, here is an aluminium plate, here is a lead slab, thick lead slab. So alpha particles from a radioactive material are stopped by even a piece of cardboard. So alpha particle cannot penetrate the cardboard. Okay. Now the beta particle penetrates the cardboard but are stopped by sheet of aluminum. So beta particle can emit the can penetrate the cardboard, but it cannot penetrate the aluminum sheet. So it is stopped by the aluminum sheet. But can see gamma radiation. Even a thick slab of lead may not stop all gamma rays. So even this slab cannot stop this gamma radiation. Hence, we can compare gamma radiation is the highest one, or it has the highest strength. Then second one is beta, and the last is alpha. Now, the different radioactive decays. In alpha decay, we have found that there is a helium nuclei escaping. So the transformation is like this: XZA is changed to Y. The nucleus has been transformed to another nuclei with atomic number Z minus 2, mass number A minus 4, and a helium nucleus. This is an example for that. Second is beta decay. This nuclei is transformed into another nuclei Y with an emission of electron. Since this is the electron emission or the beta decay, there is an increase in atomic number Z plus 1. Here is an example. Next is positron emission. Here the nuclei, the parent nuclei is changed into another nuclei Y with a decrease in atomic number with the emission of positron. Positron is an element having positively charged electron. So the charge of positron is plus E. Okay. Here is an example. Next is the electron capture. So the nuclei captures one inner shell electron and transforms into another element Y having a lesser atomic number, Z minus 1. Here is an example. Now gamma decay. This star denotes the excited nuclear state. This is the excited state, and here there is no transformation taking place, but the element is de-excited to a lower energy state. Okay, and gamma is liberated. Gamma radiation, gamma ray photon is liberated. So this is an example, right? Now, in a more detailed way, you can see the 5 kinds of radioactive decay. This is the gamma decay. This is the original nucleus. Red ones are the protons and these grey ones are the neutrons. So here is the original nuclei. So here we are considering gamma decay. Here there is an emission of gamma ray, it reduces energy of nucleus. So the final nucleus, there is no change in the number of protons or neutrons. The reason for instability was why this original nuclei is transformed into this one. The nucleus has excess energy. That energy is liberated in the form of a gamma radiation. Right? Now the second is alpha decay. You have this original nuclei. Here we emit an emission of alpha particle. It reduces the size. Here 2 protons and 2 neutrons are there. So this is the final nuclei. So the size is reduced. The reason for instability was nucleus was too large. So it emits by alpha particle radiation. Next is the beta decay. This is the original nuclei. So what happens in beta decay? This neutron, they change into an electron. This black dot is the electron and a proton. Neutron transformed into an electron and a proton, and pure proton replaces the place of neutron here. Okay, and this electron is emitted to outside. So the emission of electron by neutron in nucleus changes the neutron to a proton. Here the neutron is there, here in that place there is proton. This happens because nucleus has too many neutrons relative to number of protons. Okay, this is the reason for its instability. Next is the electron capture. So this is our original nuclei. So an electron is captured by the proton. It changes into a neutron. Okay. Capture of electrons by protons in nucleus changes the proton to a neutron. So if you consider this proton, here it will be this one. Just will change into a neutron. Right. So here what may be the reason for instability? Nucleus has too many protons relative to the number of neutrons. If there are more protons, it will be transformed into neutrons. That's the reason for electron capture. Next is the positron emission. Positron emission is like this. This is the original one. The proton emitting a positron plus a neutron. This is emitted and this replaces the proton. Here too the reason is nucleus has too many protons relative to number of neutrons. Okay, these are the 5 kinds of radioactive decay.